Welcome to the morning session. Thanks for being here early on the third day. We will start off with Itai Hen telling us about limitations of physical quantum annealers.
Thank you, and I'm really very excited to be here and tell you about my work. I'd like to thank the organizers of this so far really wonderful workshop for allowing me the opportunity to speak here. And I'm going to tell you a little bit about what I've been doing in the past year or so, maybe 2 years even. And these are my main collaborators, so most of this work was done with different combinations of these people. Victor Martin Mayor from the Complutense University of Madrid, Tamim Albash from USC, Jeff Marshall from USC, who I think I stole from Paulo for quite a bit of time. And also Brian Zheng from Stanford, Gene Wagenbreth, who is now at Cray, and our chair, Eleanor Rieffel. And so I guess the question that I've been trying to ask is, should we expect to see any speed-ups from, real quantum annealers? And I had to amend a portion of my presentation. I was going to say that given, the absence of positive results so far, and then, of course, I heard the talk by Helmut and Salvatore, so hence the comment, so excluding... yes, okay. I will tell you what I mean. Okay, so, yeah, given the... Sure. Given the limitations. So anyway, I was wondering if there are any fundamental limitations that we should be made aware of. And so this is a brief outline of my presentation. I'll start with some motivation. I'll talk a little bit about fixed temperature quantum annealers, and then go through a little bit of chaos. So there's, I guess, 3 types of chaos, which we call T chaos, J chaos, and gamma chaos. Of course, I'll explain all of them, and if time permits, I'll talk about temperature scaling law for quantum annealing optimizers. So what is the motivation? The motivation is that, again, there's no real evidence that quantum annealers provide advantages, at least if we look at them as quantum annealing optimizers. And recently there's been a lot of work, a shift towards, studying these things as Boltzmann samplers, which of course I will maybe talk about it a little bit later, but of course this is still a viable approach. Other suggestions were that we could use these quantum annealers as suboptimal, configuration finders or solvers, in which case the energy, the bar that is set for success is quite a bit higher than the ground state energy. However, I think contrary to maybe some of you may sort of think or even presented here, I think that suboptimal solutions are in most cases for practical problems are not the best thing that we can hope for from quantum annealers. Now, why is that? So the thing is that most practical optimization problems, they have constraints. And QUBO or Ising is an unconstrained binary optimization. And so what do we do to impose constraints? We add them as penalties to the problem Hamiltonian. There are other ways, but mostly that's what's being done. And so if we add them as penalties, then violations of constraints basically cost sometimes a tiny bit of energy. But if you look at the configuration, even though the energy is just slightly a bit the ground state, still the configuration is nonsensical in terms of the original optimization problem. For example, for planning, if I get a really good configuration with really good energy, but 2 tasks appear at the same time where they shouldn't be, violating a constraint, then there's really nothing I can do about the configuration. It's basically nonsensical in terms of the problem. And so I would like to claim that for real-world optimization problems in generically at least, if you allow me to say that suboptimal configurations are not really what we're after. Now, of course, a resolution to that might have been adding the constraints with very high penalties. But of course, as most of you know, by doing that, since we're always normalizing or renormalizing our coupling strengths, then what happens is that the problem parameters basically scale down into the noise, which then are affected by analog errors, or what I call the J chaos, which I will also talk about. And this is not a good idea to do that. Of course, obviously, if you want your constraints not to be violated, then you want to, pump up the strengths to infinity. But once you do that, you lose the original problem completely. And so I'd like to still focus on, even though again it's not the focus of so far. I mean, there's been a lot of talk about samplers. I would like to look at QA devices as really ground state optimizers. And so first, I'm going to assume that the quantum annealers are real, okay? They exist in the physical world, just meaning, and I'll idealize them a little bit, but first of all, I just want to say, let's just assume that the temperature is non-zero. I guess everybody here will agree with me that that's a fair assumption. And the thermal fluctuations appear everywhere and all the time. And at a zero temperature, the ideal scenario, of course, would be to reach for the annealer to reach the ground state. And at zero temperature, of course, the quantum ground state, the one that does, I guess, this right here, the black line, gives us a really unique quantum ground state, which is very different normally with what you would get. I guess the probabilities over the ground state manifold would be very different than the one that you'd get with classical methods. And this could be, even an origin for a quantum supremacy, just because quantum annealers, zero temperature quantum annealers and simulated annealers, for example, sample the ground state manifold very differently, which is, to me, it's a very interesting subject to study, to see how you can, utilize the fact that the quantum ground state is different than the classical ground state, or I guess the probability over the ground state manifold. However, I want to go back to the finite temperature case, the case where the temperature is non-zero, and let's just assume that we have this quantum annealer going from a driver Hamiltonian to a problem Hamiltonian with these strengths A of S and B of S, and we're just assuming that the annealer is ideal and really ideal for now, but only that the temperature is non-zero. So what do I mean by ideal? That the errors, there are no analog errors, no intrinsic control errors or problem misspecification. And I'm also assuming that the thermalization is instantaneous. Okay, this is like the best thing you can hope for. And moreover, what you would really want, that the thermalization will occur at the end of the anneal, where B, the strength of the problem Hamiltonian, is maximal. It's B of 1. It's the point over there. And this is, I guess, the corresponds, if the system thermalizes at this point, that you get your Boltzmann distribution of the classical problem Hamiltonian. And of course, this is the dream scenario for Boltzmann samplers. But again, I want to focus on quantum annealing optimizers. But even then, that so far the experimental indications are that that's not really what's happening. So you would hope that the thermalization will occur at the end of the anneal, but in fact it does not. And this is an experiment that we've done with collaboration with NASA. So these are two D-wave with Eleanor Riefel specifically, we've compared two D-Wave 2 machines, and we tried to ascertain the effective temperature of the device for different instances given, I guess, freeze out. And you see that the ideal betas are really way over there, very much higher than the ones that we were able to get out of it. And so it's true that I guess it's not what's happening really is not the ideal case. And of course, I think even Muhammad talked about it. I guess several people mentioned freeze out, etc. And of course, there's the idea or concept of analog errors, which also contributes to the fact that the effective temperatures are much higher, and hence the betas for both machines here are much lower. But let us assume for now that the quantum annealer is ideal. Again, non-zero temperature, but otherwise it instantaneously thermalizes at the end of the anneal. This is really something that I guess everybody would be happy with, I'm guessing. Now let's assume that our quantum annealing device, the number of edges or couplers is proportional to the number of spins, okay? And this happens in the chimera, of course, fixed degree. And this is what you would expect, I think, for any scalable, quantum annealer, unless somebody would care to object. But I guess, if we want the energy to be an extensive quantity, or the power bill to be the electricity bill to scale linearly with a number of qubits, then that's what you expect. I'm also assuming that the problems that we are imposing or embedding have a classical minimum gap. So for example, integer j's, where the gap is 1, which is also, I think, something that's the only thing that we've been doing so far because of analog errors. And given that, we know that the ground state energy is an extensive property, and it scales linearly with the number of spins. And if I look at the intensive energy, which is here it's a small e, it's the energy divided by n, then the thermal average of E for any fixed beta is, I guess, the thermal energy of the Hamiltonian divided by n. This is, of course, very trivial, but I'd like to work with the intensive properties, if you don't mind. And for these, you can calculate the specific heat, which, simple thermodynamics or statistical physics tells you that the specific heat, which is, I guess, n times the variance of this thermal average of E, remains finite as n goes to infinity for any fixed temperature, which is our case here. Now, if E, the small e, is sort of discretized in steps of the gap, classical gap divided by n, but it disperses as this property, this quantity here, the specific heat divided by n, as you can see from here, it just means that we can treat it as a continuous variable because the dispersion is much larger than the discretization. So if we look at it as a continuous variable, then this is the probability density right there, given instantaneous thermalization, as I've assumed, where psi beta of small e is the entropy density minus beta e. This is, I know, trivial for, I guess, everybody here, simple statistical physics. The thing is that the most probable intensive energy can be found by just differentiating with respect to E and equating to 0, giving us, of course, that the most probable intensive energy is the thermal average. And then we can Taylor expand, I guess, to second order this free energy density type functional. And when we do that, and we plug it back in to the probability density or the Boltzmann configuration, the Boltzmann distribution, we get that for any fixed temperature, the Boltzmann distribution is distributed as a Gaussian. And again, I think it's pretty, I guess, trivial statistical physics for most of us. Now, what does it mean? It means that if you go to the extensive variables, the energy, the energy, extensive energy, we know that it scales like n, whereas the dispersion scales like the square root of n. Now, what does it mean? So look, this is actually experiment on the D wave where we studied many instances, and for different values of n, as you can see, as n grows larger, then the distribution becomes more and more Gaussian-like. And if you look at the rate at which the average goes away from the ground state, this is residual energy, and the way it disperses, then it goes away linearly, but the sigma, the dispersion, goes away like spreads like square root of n. Now, what does it mean about the overlap or the support over the ground state manifold? It just means that it's exponentially suppressed in n because of the Gaussian. And so, and so the Gaussian treatment, which came from really fundamental statistical physics, is, at least as far as scaling goes, of at least the shapes and the scaling of the average and the sigma, is really verified, again, to that extent. I don't want to go beyond that. To that extent, it's really verified very nicely experimentally. So it just means that the overlap with the ground state manifold for large enough problems is always exponentially suppressed. And it's true actually for easy problems as well. Doesn't matter what the problem is, as long as the number of edges scales with the number of spins, and the classical gap is 1 or some constant. So we should remember, again, I'm not sure, I mean, again, as I said, that the analysis is very trivial, but people, we are all trying to find, or some of us are really hoping to find speedups with physical quantum annealers. They are all fixed temperature. And as Daniel was saying in his talk, it's important to get the true scaling, and therefore we have to have optimal annealing time, for example. So we should sort of remember that the true scaling, no matter what you find for these small n values, the true scaling eventually, I guess, has to be exponentially suppressed as long as the physical temperature is fixed. And this is not true just for quantum annealers. It's true for any fixed temperature device. I mean, I could have nothing that I've done here is quantum. I just assume that the thermalization takes place at the end of the anneal, which makes everything classical. The only difference is that people have been looking at this device or suggesting this device as solver for practical optimization for many companies, and so this limitation is pretty fundamental, and we should be made aware of it. Now, moreover, it also means that again, hitting the ground state is exponentially small. The probability is exponentially small regarding of the specifics. And as I said, the most probable energy is the one in the middle. Is basically around the mu, the thermal average. Now, if you look at this thermal average, you will notice that since the ground state energy scales with n, and the thermal average also scales with n, the energies around the thermal average also scales with n, then the energies that the quantum annealer really samples obey this relation, that they are giving you the ground state energy times 1 minus some epsilon, where epsilon is a constant. And as many of you know, that to do that is very easy with a PTAS algorithm, because I can do this for any epsilon. I guess the complexity is exponential in epsilon, but as far as n goes, I can sort of sever the ties for cut the original problem to many very much easier problems, but just disregarding edges like so, and this basically means that I'm maybe losing some energy, but not much. But the problem becomes exponentially easier, and so there is a PITAS algorithm that actually generates the same energies that D-wave generates. Not, it's important to stress that not at the same sampling distribution, which I guess it's important to understand that these quantum annealers may be very good boson samplers, but as far as energies are concerned, I guess the quantum fixed temperature quantum annealers are bound to give us sort of trivial energies in that sense. And now another thing that I want to say, that of course all this treatment was asymptotically as n goes to infinity, but of course for practical optimization problems we don't really care about infinity. I mean, for many problems infinity means the practical regions, but maybe for many other problems infinity means something that we don't care about. And if we have a company who uses quantum annealer and they don't care about infinite size problems, they don't only care about problems with 5,000 bits, then maybe this does not apply. But again, I think it's worth remembering that at least asymptotically, if we scale up, and of course we've been scaling, or D-Wave have been scaling up for years now, so it's important to take this into consideration. Now, apart from that, there is another thing that I'd like to discuss, which has, I guess, something to do with the previous topic, but it's also very different, which is T chaos. T stands for temperature here, and this is something quite different. T chaos actually came from, or is something from classical physics for springless theory, that tells you that it's a phenomena that appears when solving spin glasses. And before I go into that, I want to sort of explain where it comes from. So if you want to solve a problem classically, then you normally the state of the art, the most general, at least for general problems, the state of the art is parallel tempering. Some would tell you maybe population annealing, but it's the same in terms of I could have done everything for population annealing, but parallel tempering is, I think, more in the forefront. And so when you look at a parallel tempering to solve a classical spin glass, what you do is you run parallel copy or independent copies of the spin glass with Metropolis algorithm at fixed temperatures, and then the key with parallel tempering is that you swap temperatures between replicas, or I guess I'd like to think of it of swapping replicas between temperature, and this turns out to be much better than simulated annealing because it allows, by replica is going to low temperature and high temperature, it allows for local search at low T and like global search in high T, because high T you accept many configurations, you can hop around. Low T means that you're more greedy, and so each replica performs a random walk in temperature space, and it means that if you want to thermalize the spin glass, then the replica has to sort of visit all the temperatures, and this is a very good example for a replica visiting all the temperatures. However, for some problems, it's very nice to see that for some instances, when you do parallel tempering and the length scale is shorter, then you see that there is sort of an invisible, I guess, line that some temperatures for some configuration at certain scale times, they don't go across, and I guess they're not ergodic in temperature space, meaning that it's not thermalized, and so the mixing time, the time that it takes to go up and down the temperature mesh, it can be very long. Now, why is that? Again, I showed you, I guess, why is that in the sense that the replicas cannot go across certain barriers, but why is that? And this is attributed to temperature chaos or T chaos. And this means that if you look at the dominant, even free energy configurations at temperature T and a temperature T minus delta T, then the dominant configurations are very, very different. And this is sort of a random phase, a first order phase transition that happens there. And so a respective minima, at T minus delta T are very, very different. And so the acceptance rates for these configurations are small, or I guess they go back and forth, and they don't really go across. And this just means that the mixing time, the time that it takes the replica to visit all the temperatures, is very long. And the question that we asked ourselves is, this is a purely thermal classical showstopper, or something that really hampers the performance of thermal annealers. And we said, okay, D-wave or any quantum annealer, but it would be interesting to see how quantum annealers respond, or how susceptible they are for this purely classical showstopper, or purely classical hurdle. And how did we do that? We generated, and this is, to us, it was a way to determine whether, how quantum annealers use the quantum features versus thermal features. Because if they use thermal features, and they are very susceptible to temperature chaos or to long mixing times, then they are more thermal-like, or they are affected by thermal thermal effects quite a bit. And so we generated very many D-wave embeddable random problems, like hundreds of thousands, and we found the mixing time for each and every one of them, and this is the probability distribution. And many instances had very low mixing times, meaning they were classically easy, and most of them had like a medium size mixing time, but some problems had a very long mixing time, and so we were able to find sort of 5 orders of magnitudes of mixing times with different probabilities of occurrence. But anyway, we took sort of 100 instances from easy problem, 100 instances from slightly harder problems, 100 instances for yet harder problem, and really 100 instances for really hard problems. And we looked at the performance of D-wave for these problems, and these are the results here. So what I'm showing here is the performance of different algorithms, performance meaning runtime to solution, versus the classical hardness or mixing time. And the black line here is parallel tempering. The slope here is 1. This is a log-log plot. The slope is 1, just because this is how we defined classical hardness. And we really did expect the D-wave slope to be much smaller, just because we assumed that thermally it doesn't use the thermal effect, or is not really affected by thermal effects. I guess we expected to see quantum effects going on, so maybe we didn't really expect it to be susceptible to thermal classical hardness properties. But this is the red line here, and as you can see, the slope here is 1.73, is much larger, meaning that at least for this, the D-wave device is more susceptible to classical hardness than parallel tempering, meaning that if I go 5 orders of magnitude for parallel tempering, it goes 8 orders of magnitude harder for D-wave. And so it was really hit us by surprise, and we did not understand why it might happen. So we tried to speculate a little bit about that, and we try to understand whether it has to do with the analog nature of the device. And this is the next, I guess, topic. I don't have very much time, but I think it's an important one to be looking at. Anyway, so this figure basically shows what happens if you run instances on the D-Wave, the same instance, but for many, many, many programming cycles. And the difference between each programming cycle is basically these analog errors, or the intrinsic errors, or the fact that the parameters that you intend to program are not the parameters that you really are programming. And if you run the same instance for many programming cycles, what you see is that for certain instances, for example, the red one here, there is a peak at a certain probability, meaning that most programming cycles give you the same probability, which is what you would expect, of course, just because you're running the same instance over and over again. However, for other instances, the blue instance, the probability density over success probabilities is pretty flat. It just means that, you know, for 20% of the times that I run the same instance, the probability is high, and for 20% is, you know, medium, and for 20% it's very low. But I'm running the same instance, so it could only, I guess, come from analog errors. And of course you could tell me, well, maybe it's not the analog errors, maybe it's just the statistical, you know, it's a statistical binomial Bernoulli experiment, and the only difference is just can be explained by the statistical nature of the experiment. And we try to understand whether or not this is true. And let me show you what we did in order to ascertain whether or not it's true. We know that depending on how many annealers we're trying, we can ascertain the standard deviation, assuming that there are no analog errors. We can ascertain the standard deviation or the spread just by from the statistical nature, whereas we can also calculate the actual spread by running the same instances over and over again, and we can look at the ratio of the actual spread versus what you would expect just from statistics. And what we get is that for a tiny, small fraction of instances, and this is exactly what you're seeing here, actually for two machines, the NASA machine and the USC machine, and what we found is that for most of the instances, the statistical fluctuations were not able to really account for the fluctuations in probability, success probabilities. Which means that J-chaos, or J-chaos is what I call the chaos that comes from problem misspecification. And again, the reason I'm calling these things chaos is not just because I like the names, because the tiny differences in the J's or in the temperature or whatever cause huge effects. They are very detrimental in a sense to the performance of real quantum annealers. And again, we did our experiments on D-Wave devices, but only because I guess they're the only ones out there. But this is true for any analog machine, any quantum annealer. This is true for temperature chaos and J chaos and everything I've said so far. So it's nothing about, it's just what I would call a fundamental limitation of quantum annealers, just because they're analog, just because they're fixed temperature, and so forth. So it's important for me to say that. And I wanted to, I guess, how much time do I have? Not much. Okay, so I'm gonna actually I've done some analysis on the errors, which is pretty, to me, is pretty interesting. What I guess calculated I injected errors, artificial errors into the machine by changing the coupling strengths by just injecting Gaussian errors, and basically what you find is exactly that that the probability densities, or let me show you here, that as you increase the magnitude of the error, the problems become more Gaussian-like, but also they move away, of course, from the ground state, meaning that obviously the performance is deteriorating with more and more error, and the effects are, in 1 minute I will say that the effects are in a sense exponential to the ground state energy. This talk is about quantum annealing optimizers, not about anything else, and it's important again to understand because you can use it in samplers and so forth, and really this is not about that. And skipping ahead, I just wanted to say something about another special type of analog chaos, which I call gamma. Gamma means it's a uniquely quantum chaos. It's a transverse field chaos. It comes from, I guess, what happens if you move at zero temperature even from the driver Hamiltonian to the problem Hamiltonian. There too, you can expect, and this was a nice work by Sergei Kanish in 2016 that shows that if you go through the spingless phase, that you end up seeing random anti-crossings with exponential suppressions, and they could be very many of them. And this is the quantum analog of temperature chaos, but it happens in the quantum parameter. And this is also something that mostly overlooked. And this also tells you something about the freeze out, that if there is a freeze out before these I guess gamma chaos or gamma first order phase transitions, then the configuration that you get once you have freeze out are very different than the ones at the end of the anneal, which is really a problem. Okay, I was really optimistic there. I'm gonna just conclude. So there are numerous fundamental limitations to physical quantum annealers. I think they are normally pretty much ignored, but they really shouldn't be. And again, while the treatment is asymptotical, it may not mean all that much for finite size problems, which may be of interest to the non-scientists of us. And the limitations apply more to quantum annealing optimizers than to samplers, and they can be mitigated via the usual suspects like lowering the temperature, reduction of the intrinsic controllers, and maybe error correction schemes. That's it. Thank you very much. Thank you.
In the first part, you said that it is hard to find the ground state energy because the distribution, the expectation value is proportional to the system size, extensive, and the standard deviation is proportional to the square root. Yes. By showing the evidence. Mm-hmm. But, well, that itself is true, of course, it's elementary. Right. But probably the problem is that you are looking at the average energy, and the Boltzmann distribution gives the largest probability for the ground state. So if you look at each sample, and then you will find the ground state with the largest probability.
Okay, I'm not sure I follow, but okay, I will.
Okay, so I have two questions. One is related to, when you compared with the p-TANs, you said this is polynomial in the side.
Yeah, I didn't compare, but I just mentioned that the p-TAS gives you, the energies that the fixed temperature quantum annealer would give you.
Yes, but do you know if the scaling with respect to the epsilon is going to be the same for the finite temperature annealer and a p-TANs, like you see what I'm saying? That do you know?
Yeah, so I mean, I really sort of did a favor to quantum annealers by assuming that the thermalization is instantaneous at the end of the anneal. So meaning that I was just assuming that the runtime is 0 and to get these energies, and I did not look at I guess the actual runtime that would happen. And what I suspect is that p-TAS for any practical purposes will be much worse. However, there are other algorithms. PITAS is not, nobody uses PITAS. There are other algorithms that do the same. PITAS is just proof. There are other algorithms that could do much better. The only reason I'm mentioning PITAS is just because it tells you that these energies are easy to generate.
Okay, so second question is related to the main plot that you had that, you know, based on power tempering, you characterize hardness of instances and you observe that D wave has a worse slope.
Yes.
And I think it's a very nice study, but I don't agree necessarily with the conclusion is that you're saying that this is a signature of that D wave doing thermalization in a way?
No.
What it could be like many-body localization, for
It
example,
could be
quantum effect.
all I'm saying, and all this figure was showing, is that D wave is affected more harshly than parallel tempering by temperature.
No. That's the thing. I don't agree with that because how do you know it's the effect of temperature? Because the
Because
instances
this is the only difference between. This is how we set up the instances.
No,
this
but
this is the only.
we can discuss it after I disagree with that.
Sure.
We could be other.
I'm really sorry, but